This meeting is being recorded.
So we are going to go to the experiment that is called entropy and enthalpy together. What do they do? And that's what Joshua was trying to get to, but it was a little too early. Here we are. What happens with entropy and enthalpy? Are they going to go together? Are they going to, if positive entropy means positive enthalpy, or negative entropy means negative enthalpy all the time? Is there something else involved? Yes, the temperature is involved, we know that. But the temperature is involved in a quirky way, not directly. So that's a little bit difficult thing to do. But we're going to talk about that. What does it mean? Entropy and enthalpy together. So let's see. Balancing enthalpy and entropy. So this is what we have in your student view. So this is what you will be seeing. And this is the report you are going to do according to this. It took me 4 hours or so to prepare this report. So please use this report. In some ways,
Professor, is this report in files?
yeah, it's also in the file. Some ways, teaching this class is like teaching chemistry 1A for me for the first time because of this requirements that are added because of teaching on the online. So I have to look at all the different experiments that we are doing a virtual experiment, which I have not done before. Virtual experiment, I have hardly done any. So, and then I look at that and I say, what is important and what needs to be changed, what needs to be added over here so that the student have a better idea of what's going on. And for every experiment, I have been doing that. That takes 3-4 hours to do that. Anyway, but I was pleased with what I did. So that's what counts. So here it is. Do Tuesday, March 30th. So next week, you have a week to get this done. And what are you going to do? That's what we're going to talk about. A reaction is spontaneous from products and form products when delta G, this is means delta. I try to change it, but it just does not change that damn thing. I try to change it. It should be delta H like this, delta G. Delta G. Well, we are talking about something else here that we have not talked about. Delta G. Delta H we know. Delta S we know. But when we put this delta H and delta H together, or when we try to understand them together, there is something else happens. A new state function is produced. How is that going on? So first, we want to understand sign of delta H and sign of delta S, and we did that. And here are the thing that we already did with sign of delta H and sign of delta S. So you are going to copy that from what we did today. These are the reactions that we talked about: solvation, and equilibrium and all those, sign of delta H and L. And please try to make a table out of this. I understand that, and you understand that these tables don't stay together even when I make them. So just put with a ruler, put a line here, put a line over here, and make some lines to our table. Anyway, so this thing, we just now did that. Process or reaction. This is a reaction. This is a reaction, but this is let's see. This is a process. This is not a reaction. Solvation is a process. It's not a reaction. No changes are happening in solvation. So in equilibrium, there are reactions happening, but they are both canceling each other out. Okay, so that's heat of reactions and entropy of reactions. And this delta G business, we are going to talk about it soon, but not here. So let's see what's here. Yeah, we got all discombobulated over here. Yeah. Okay, let's see. I will have to show this to you. This is what it should look like. And I tried to not get it discombobulated, but it did. I did it a couple of times. Took me a lot of time to do that, but then I thought it would do it, but no.
Okay.
So write this down here. Oh, my dears, write this down here. Let's see, what do we have? Draw. So, yeah, if I draw that, that's what happens. Now, this business of DG, it should be like this, of course.
Hey, Professor,
Yes.
I think the file that you have on file for the balancing is different than that.
The file that is different than this?
Maybe not. No.
I hope so, because I tried to change this DG and stuff like that differently. I hope that went in there.
It didn't, but it's got the same thing. I just never mind.
Okay, so I hope it is a slight bit different. It's better than this. That's what I hope. Yes. Okay, so here we are. So what do I want? You want delta here, this kind of delta. Delta and delta and D delta S. Okay. Let's go back and talk about how these are, well, balancing enthalpy and entropy, and how what happens when we try to balance that, or what does it mean to balancing enthalpy and entropy anyway? That means how are they going to affect the reaction? What do you mean by affect the reaction? The reaction either is going to go on or not go on. Some reaction happens. When we mix two things, not necessarily there is going to be a reaction. Sometimes there is a reaction, sometimes there is not. Sometimes we'll look at the net ionic equation to see if a reaction really happened or not. There are other ways to look at it too. So, when a reaction happens, we know that the S value of the surrounding of the universe has to increase. This is one thing we found out, that if a reaction increases, the surrounding value of entropy, then that reaction seems to be happening, meaning that reaction is spontaneous. We don't have to put energy into the system in order for the system to react. What does it mean, spontaneous? Spontaneity, spontaneous, something that happens without any interference. That's what a spontaneous thing is. So when we talk about a chemical reaction that happens just because we mix two things, that's a spontaneous reaction. If we mix two things and the reaction does not happen, we have to put energy into it for the reaction to happen, then that is not a spontaneous reaction. For example, matches. Matches are not spontaneous. In order for this match to light, for the reaction to happen, we have to strike. And that is putting energy into the system. Only when we put energy into the system, that's when the match lights. And that is called not a spontaneous reaction. But once upon a time, there were matches that would ignite spontaneously. Once upon a time, 150 years ago, they had matches. The match would just catch fire on its own, sitting there on top of your table, and suddenly there is a fire going on. Now, nobody likes that kind of match, but it was better than what it was before that. Before that, of course, you might remember that you have to have a burning something in order to fire to start, or you have to have that contraption where you are going back and forth with I don't remember what it is called even. Anybody remembers what that thing is called? To make, you have a thing that you can move with two hands. There is a. Sorry, what?
I know what you're
What is it
talking
called?
about, but I don't know the name of it.
Yeah.
I've used one before. It sucks.
Oh, okay. So yeah, everybody knows. I mean, but the match was better than that. But the match has a problem. Your whole house could start burning. So now that match was not a very good match, but it was better than that. All right. So then some people said we need to make sure that this reaction is not spontaneous. Sometimes we want our reaction to be spontaneous. Sometimes we want our reaction to be not spontaneous. So we need to understand when is a reaction spontaneous and when it is not spontaneous. And enthalpy and entropy both plays part in the reaction, in the spontaneity of the reaction. So that's why we need to look at both of them together and see how they affect the spontaneity of the reaction. And anybody can understand knowing about the spontaneity of the reaction is very important. So that's why today we have matches that are not spontaneous, and we are very happy with them. Now, when these matches were discovered, they had a slightly added name to them. They were not called matches. They were not called just matches. They were called safety matches. Safety matches. Because these matches were safe. They were called safety matches. And the other ones, not safe matches, pretty soon people stopped using them. Pretty soon they were forgotten. And so pretty soon these safety matches, we don't call them safety matches anymore. We just call them matches. And most people don't even know that, this once upon a time we had matches that did this nefarious thing, bad thing of igniting themselves on their own. So spontaneity is very important. We want to know how enthalpy and entropy are involved in spontaneity, and this is the experiment is part of that. So in order to understand, first we have to understand the delta H and delta S signs. How are they changing, or how to assign signs to a specific process, and we did that. We now know how to assign delta H and delta S sign to a specific process. And we can also calculate it. So that's what we're going to do, a little bit more calculation. That's what we are going to do. And here I need to change this. This is supposed to be that. Sum of. Instead of that, that became S. Sum of. Now, we are going to calculate these two things first, and we are not going to talk about this right now. We will a little bit later. We're talking about the reaction, glucose burning. Everybody knows glucose does not burn on its own. It is not a spontaneous reaction. You have to put energy into the system, into glucose, in order for it to burn. So this reaction is not spontaneous. We know that. Now, let's look at what is the heat of reaction is. And that heat of reaction answer should be there. So we just gonna do the simple math, addition and subtraction. Heat of formation of products. Heat of formation of products, what is it? Yeah, that other thing is different than what I have given you over here. I'll have to change that. I don't know how that happened. Okay, let's go back over there. Leave the student view and go back to that. I hope that is better. I don't have to write it. Files. Okay. Oh, what happened? Oh, there we go. Okay, this looks like what it's supposed to look like. Okay, good. In the file, that's where it's at. All right. And I hope your file looks this way too. That's something I did not check, but you can check it. So we did this already. You should be able to write down, and I want you to write down, and in the report, you are going to put this down again. And then calculate this. This is what we are doing, calculating. Just calculating this one. Now, still there is a little problem here, don't it? Yep. Still there is a little problem. Okay. So we are going to calculate heat of reaction. And we have the heat of formation of 6 mole of carbon dioxide. That's this here is the heat of formation of carbon dioxide. So we're going to multiply that by 6. Okay. 6. And in this case, if you just multiply by 6, it's okay. If you don't write 6 mole over here, I'm not going to quibble about that. Normally, we would write 6 mole and then minus 393.5 kilojoules. That's a lot of energy per mole. And mole cancel out. So that's 6 multiplied by that kilojoules is what we have the answer. And then we have water as the product, not water, vapor. Water vapor, the gaseous water is a product. And that's heat of formation of gaseous water is this. So you're going to multiply by 6 of those because 6 mole in the product part. So we're going to see, put it in the parenthesis, plus this is plus 6 mole of this. And when I do that multiplication, 6 multiplied by 241.8 equals negative. That is a negative thing, of course, you know that, negative 1450.8. 1450.8. kilojoules. No moles. Moles are gone. Then minus, that's the minus, this here minus. These are the products. Now we are talking about the reactants. We have two reactants here, glucose and oxygen. 1 mole of glucose, and that is 1273 kilojoules. So I'll write that down. Negative 1273 kilojoules is just 1 mole. So I don't need to say moles, joules per mole or kilojoules per mole or anything like that. Now, what is the heat of formation of oxygen, 6 mole of oxygen? Can anybody tell me that? What is the heat of formation of oxygen?
Yeah.
0, because it is a element in its natural state at 25 degrees Celsius. So that's 0. So we're gonna add and subtract. Be just a little careful. This is gonna become negative, become positive here, and this is gonna be negative, and this is gonna be negative. So this is negative number. This is gonna be a positive number, and when we do that math, we get to this. Now we are going to do the enthalpy of the reaction. So this is the equation. N means number of moles, and this is a sum of. So we want 6 moles of carbon dioxide, enthalpy of carbon dioxide multiplied by 6. I'm sorry, entropy of carbon dioxide multiplied by 6. Entropy of water vapor multiplied by 6. And then subtract entropy of these two. So let's see. Somebody is going to Google. Let's see who is going to do that. Makaya, Google the entropy of carbon dioxide, please.
Let's see. 215.
200 and what?
213.7.
213 joules per Kelvin. Is that correct?
Yeah.
Okay. So here we have, and then these are 6 moles, so I'm not going to write this mole. We are just going to say, okay, that got canceled out. Joules. Okay. Lisa, look up the entropy of H2O gas.
I have. I don't know if this is right, but it says 188.8
That is correct.
SOJK times mole.
Yep. 188.8. What are the units?
S to the 0, so 25, and JK times by mole.
So joules per Kelvin and mole. Kelvin multiplied by mole. Right? Those are the units?
That's what it says.
Okay, and so we have 6 of those. We're going to say 6 multiplied by that. And the entropy values are always going to be positive. They are never going to be negative for a particular substance. For the reaction, entropy value can be negative for the whole reaction. Okay. Minus entropy of oxygen. Zachary, could you look up entropy of oxygen gas?
It says 205
205. And what are the units?
joules per Kelvin times mole.
Kelvin times mole. And we're gonna forget because we wrote mole over here, 6 mole. Okay. And minus 1 mole of glucose. So Ethan, look up the entropy of glucose. Just ask the question to Siri or to Alexa, whoever you have.
It's 212 joules over Kelvin.
Can't hear you.
212
212, and what are the units?
joules per Kelvin.
Very good. We're not gonna write that mole right now. And when we add this up, we get this answer, 973.8 joules per Kelvin. No moles here. Moles are all canceled out. Now, so these equations are there. You don't have to memorize them. You have your book. You have to realize which equation to use. That's what it is. And then it's pretty simple, just multiplying, simple thing, and adding and subtracting. Now, we're not going to talk about this right now. We're going to go further. So now we know how to, we have practiced a little bit about how to calculate delta H and delta S. Calculate heat of reaction and calculate enthalpy and entropy of reaction. So we go to next. Now, the main thing is spontaneity. That's what we are after. Now we can talk about spontaneity because we understand that there is a relationship between delta H and delta S. And that relationship is going to decide whether some reaction is spontaneous or non-spontaneous. And we know, we want to know about, sometimes we want a reaction to be spontaneous, sometimes we don't. And it is important to know when that is the case. So with respect to this, to that spontaneity, delta G refers to spontaneity. And delta G has a name. It's called Gibbs free energy. It's called Gibbs free energy. What does it mean? Gibbs is the name of a scientist. American scientist in the 1850s came up with this idea. Free energy. No, nothing is free. You have heard that before. Nothing is free. So what do we mean by free energy over here? We mean energy that is available to do work. A chemical reaction, exothermic chemical reaction, would provide energy, but only some of this energy is available to do work. Other is not. We take an example of the automobile. In the automobile, we are doing chemical reactions, and these chemical reactions are providing us with a change in temperature and a change in volume. And the change in volume of the piston is what is, of the cylinder, is what is moving the piston, and moving the piston changes the volume of the system. And first of all, when the gasoline burns inside the cylinder, it increases the pressure. Why does it increase the pressure? Because now we have many moles of gas produced instead of liquid. A little bit of liquid produces many moles of gas. And so this pressure is increased, and in this increased pressure is able to move the piston. So I want you to visualize what is inside happening in there. Let me show you. So a car has engine has cylinders. Cylinders are like this. Cylinders are like this. This is a shaft. And the gasoline is injected in this cylinder. There is oxygen and gasoline, mixture of oxygen and gasoline injected in the cylinder. There is a spark plug that is going to produce the spark. And because of that, this gasoline liquid is going to burn. And when the gasoline liquid burns, it produces carbon dioxide and water and other stuff that we don't like. It's not all carbon dioxide and water, unfortunately. It's also some pollution that happens. But anyway, most of it is carbon dioxide and water. And both of these are, carbon dioxide and water vapor, of course, at very, very high temperature, 450 degrees or somewhere there. So these are gases, and the gases occupy a lot of more space than the liquid. So, and also these gases are very, very high pressure, high temperature. So these are going to have very high pressure. Suddenly the pressure in the cylinder is going to increase when the reaction happens. Now the pressure increases, that is going to push this piston down. And now the piston is going to go over here. The new position of the piston is going to be over here. This is the new position of the piston. That means this shaft moved. Now, the movement of the shaft is in straight direction. There are gears that are used in order to make this into a circular movement of the wheel. That's a mechanical thing. This is the chemical thing here. This is a mechanical thing. So what is happening here is that the pressure is increasing, and the increased pressure is going to push the shaft and increase the volume of the cylinder, and that shaft is going to be used, the motion of the shaft is going to be used into converting it into the circular motion of the wheels. That's the idea. Now, this energy that is produced by this reaction can be calculated. And actually, it's not that hard to calculate. Just like this, we just write down which reactions are main reaction, and just delta H for all the reactants and the products are there. So we can calculate that. So this is calculated. But all of this delta H is not used in order to move the piston. Only some of it. Because some of this delta H is going to be converted into work. Remember, Q equals, E equals Q plus W. Q plus W. The energy that is produced by this reaction going to go into two things: heat and work. The work is the movement of the car, and the heat is going to go out of the engine. Of course, the engine is very hot, and part of that energy is just going to dissipate into the surrounding. That's what's going to happen. So the energy of the burning of gasoline is this, but all of it is not going to be converted into work. Only part of it is converted into work. Part is just wasted as heat. Wasted. Heat just goes out. How much of it is converted into work? This is our question, because work is what we are interested in. And that can be calculated by Gibbs free energy. And its symbol is G. So this work that is done by this chemical system, that how much of this energy of the chemical system is going to go into doing the work, that can be calculated by Gibbs free energy. So that's why Gibbs free energy is important. So Gibbs free energy is also connected directly with spontaneity of the reaction. If the reaction is spontaneous, Gibbs free energy is negative. Delta G is negative. If the reaction is non-spontaneous, delta G is positive. If the reaction is in equilibrium, like the reaction we had earlier, like the process we had earlier here. This is in equilibrium, this process, delta G is 0. So for a spontaneous reaction, delta G is always negative. For a reaction in equilibrium, delta G is 0. For a non-spontaneous reaction, delta G is positive. Now, how is this delta G connected with delta H and delta S? We are going to go back to it again. Now, when we talk about delta H and delta S, we know that there are 4 possible things. You can have negative sign of delta H, positive sign of delta S, positive sign of delta H, negative sign of delta S, negative sign of delta H, negative sign of delta S, positive sign of delta S, and positive sign of delta H. Those are the 4 possibilities, the sign wise. This is what's possible. So we want to compare, we want to look into the contribution of enthalpy and entropy into spontaneity of a reaction. Then we have only these 4 things to consider. We're not going to talk about zero equilibrium, then there is nothing happening. I mean, no energy is coming out, so we don't care about that. Okay, so how are delta H and delta S connected with each other, and how are delta G? So that is the equation for that is here. Delta G is delta H minus T delta S. Delta G is Gibbs free energy, is the energy that is available to do work. Is the sign of which tells us whether the reaction is spontaneous or non-spontaneous or at equilibrium. That's what it tells us. And we'll talk about this, how this equation came about. We'll talk about more about that later. Right now, we are going to concentrate on the experiment here. So this is the equation, and let's look at the equation. What are the units of delta G? Anybody should be able to tell me what are the units of delta G by looking at this. Okay, let's make it simpler for you. What are the units of delta H? Everybody knows that, so tell me please. Units of delta H is an energy. What are the units?
Joules per mole.
Yes, kilojoules per mole, or joules or kilojoules, doesn't matter. But we like to have kilojoules for, because joule is a very small unit. Kilojoule per mole. What are the units of delta S? Look at your notes and tell me that. Delta S.
Kilojoules per Kelvin.
Kilojoules per, and here we are going to have joule per Kelvin because delta S is usually much smaller than delta H value wise. So just we are gonna say joules per Kelvin and then mole. And this is multiplication multiplied by Kelvin. Now tell me what are the units of delta G? Anodidai say, what are the units of delta G? If you don't know, you say, I don't know. I guess Anodidai, so he's not there or he does not know. Okay. Michael?
I'm not sure.
Okay. Michael, tell me, when we are adding some things, can we add things with different units?
Oh, are you asking me?
Can we add things, can we add joules to temperature?
No.
No. What are we adding here? What units are we adding together or subtracting? Same thing.
Joules and moles?
Yeah, joules and moles and that's right, joules per mole, right?
Mm-hmm.
Because this canceled out. Kelvin
Mhm.
canceled out with that T. T is going to be Kelvin. So here we have K here, K multiplied by this, and then we know that the K is canceling out. So we are ending up with joules and kilojoules are the same thing because, it's just,
Yeah.
yeah. So now you are adding these two units. What are the units of the answer, please?
Kilojoules?
Yeah, same thing, right? You
Yeah.
cannot add, if you are adding two things, they have to have same unit, and the answer has to have same unit. So delta G what are the units of delta G? Kilojoules per mole.
Kilojoules per mole. Okay.
Those
Gotcha.
are the units of delta G. And that makes sense because this tells us that delta G is energy, because energy is measured in kilojoules or kilojoules per mole. So delta G is energy. And what is the name of delta G? Gibbs free energy. Well, of course, it's called Gibbs free energy. So it has to have units of joules or kilojoules. And mole is just, we talk about chemistry, so we say mole. Otherwise, we don't even have to say moles. So that makes a lot of sense. Now, we calculated this too. If we want to calculate delta G, we have this equation. And I have not derived the equation for you yet. It's a relatively simple equation, but we'll do that later. So this, we're just gonna do delta H, which is this one. And we're gonna go tax negative 2.539. Let me write it down, 2,539 kilojoules. And minus T delta S. Can somebody tell me the value of T? What is the value of T here? Temperature. What is the value of temperature over here? Joshua?
The value of temperature?
Joshua, what does this mean? This 0?
Yeah, it should be 25 degrees Celsius.
No, it's 25 degrees Celsius. We're going to convert it into K, 298 K.
All right, perfect.
298 K. Multiply that with this. 973.8. 973.8 joules per K. And joules per K, now we're going to cancel out K. K and K canceled out. So we are ending up with joules. These are kilojoules and these are joules. So now we have to do a little bit math in order to deal with that. Convert one into the other or whatever, however you want to go. Usually we like to have the answer in kilojoules because these joules are too small. So we convert this into kilojoules. So that's going to be 0.9738. No, multiply by 298. I need to multiply that, forgot. Okay, 298 multiplied by 0.9738, convert it into kilojoules. 290, I want 4 sig fig. 290.2 kilojoules. So minus 25, 39 kilojoules, minus 290.2 kilojoules, 0.2 kilojoules. So something got screwed up. 290.2 plus 2539 equals 2829 equals 2.829 kilojoules. What happened? I did not get it. 2.829 multiplied by 10 raised to 3 kilojoules. Very lots of energy. When glucose burn, a lot of energy is produced. We saw when sucrose burned, there was a lot of energy. We saw that demonstration. So glucose and sucrose are very similar, of course. There is a lot of energy produced. This much energy is available to do work. If we burn glucose, not all of it is energy is available to do work. This much energy is available to do work. Now,
So energy, is it always going to be positive for that case?
now this is going to be negative, of course.
Okay.
Thank you. Minus this. And this also means that this is a spontaneous reaction. Once the sugars start burning, it's a spontaneous reaction. It's going to only stop. But you have to start the reaction. Sugar reaction, start the reaction. But when it start burning, it's a spontaneous reaction. That's why the negative sign is there. That's what it means, a spontaneous reaction. And this much energy, a great amount of energy is available to do work. This is what we understand, available to do work. So we have done the calculation and we understand to a certain degree what delta G is about. So let's look at it further. This here is the experimental part. And I am going to ask you to do the experimental part on your own. There are 3 reactions that you will have to go into the Beyond Labs and do the 3 reactions. And by now you have an idea how to do those things. They are relatively simple thing, won't take much time. So this time I'm gonna say you do it. The only thing is that there is 1 or 2 people who do not have access to Beyond Lab. Now, you guys, you need to speak out right now and tell me that so that I can make some arrangement for you to do this. So is there anybody here? Is there anybody here? Is there anybody listening who cannot have live Beyond Lab and cannot do this lab on their own? Everybody can do their lab on their own on Beyond Lab. That's what it means?
Yeah.
All right, that's what it means. Then I'll leave it there to you. Now we're going to talk about. So you will go into Beyond Labs. You will go into this lab, entropy and enthalpy, and you'll follow the directions. And there are directions like, we have done this kind of thing before. Put it into the calorimeter. Put this much thing into the calorimeter and do this and measure the temperature. And then that's that. Okay, so you're going to write this down, mass. You're going to write down the initial temperature. You're going to write down the final temperature. You're going to write down delta T. And remember, delta T, you are not going to add 273 to delta T. Because when we are talking about delta T, Kelvin and degree Celsius is the same thing. Write it down again if you need to write it down, but have that together. Only 1 or 2 students did not do that. Otherwise, everybody else in the homework did that. So that was good. Molar mass, NaCl molar mass, everybody know how to do that. Experimental delta H of solvation, heat of reaction. Solvation means dissolving. This is not a reaction, but we call it heat of reaction loosely anyway. Heat of solvation, experimental. So you are going to calculate Q, because you have mass of the whole thing in the calorimeter, 200 point some grams, and then you know the specific heat capacity, and you know the delta T, so you can calculate Q. So let's see, remember the calculating Q, we do it like this. Q equals mass multiplied by delta T multiplied by specific heat capacity, and this is going to be water like, so they will tell you that you just use the specific heat capacity of water. And so you know how to calculate Q. We have done that in the lab before and otherwise. So that's a simple thing. So calculate heat Q. That you're going to write it down over here for these 3 processes. And then molar mass of NaNO3 and sodium acetate, you write that down. And experimental delta H solvation, you just, we have done that too. How to convert Q into delta H? One simpler way, you can do a simple 1-step dimensional analysis, or you can just remember that the units of delta H are per mole and the unit of heat are kilojoules. So you just divide by moles in order to get to heat of reaction, from Q to heat of reaction. To go from Q to delta H, just divide Q by what? Mole.
Molar mass.
That's it, because this is kilojoules per mole. Kilojoules per mole, and this is kilojoule. So that's very simple. If you don't do that 1-step dimensional analysis, I don't mind that. Remember, I have told you, you don't have to, if the dimensional analysis is just 1 step, you can just do it in your head or do the calculation on your calculator and write it down. That's okay. So that's how you are going to find the kilojoules experimental heat of solvation here. This is experimental because you are doing virtual experiment. So this is done experimental. This is your experimental value. And then we are going to give you the true value and you are going to calculate the percent error. That's one of the things that you are going to do for this lab. So that's written down later. Here, write down your experimental heat of solvation. This is where the experimental heat of solvation, for only one of them we are going to do. You are going to calculate all 3, but you are going to show the percent error for just one of those. That's all. So here it is. Here, write your experimental value. Here, write the theoretical value of heat of solvation. And how to find that, we'll talk about that. That's just what we did earlier. That's simple as that, but we'll also look at that. And the percent error is this, so you can find the percent error. So that's part of the experiment. And then the other part of the experiment is to write down. So finishing doing this and then filling up this this table and then filling up this table. So we are going to do calculation together for this one thing. So what are you doing right now? I want everybody to calculate the for this reaction, NaCl plus H2O, solvation of NaCl solid, dissolving NaCl solid. Find the delta H reaction, the standard enthalpy of reaction for this reaction. And what is given to you right here. Calculate delta G, but in order to calculate delta G, we have to calculate delta H and delta S first. So because remember delta G is delta H minus T delta S, and T, or everybody knows this T, it is 25 degrees Celsius because this superscript 0 tells us that. So if you want to calculate delta G for this reaction, then you need to calculate delta H and delta S first. And that's what we are doing here. Calculate. So first calculate delta H solvation, true value. This is your true value because it came from calculation. This delta H value right here is your experimental value, and that is going to go over here. Experimental value, the theoretical true value is from here, calculation here. And that you're going to calculate right now. You are also going to calculate delta S for this, only this reaction right now. The others you will do it later. And then we don't know the temperature change. So we are just right now, you are calculating delta H for this reaction, and delta S for the reaction right here. That's what you are doing. So this is part of the lab work that you are doing. And this is 1 point right now. And I'm going to help you with that. So anybody has any question while you are calculating this, I am available to do the help. So, okay, everybody, what is given here? Heat of formation of NaCl solid is given here. Heat of formation of sodium ion is given here. Heat of formation of chloride ion is given here. This is the reaction. And ignore H2O liquid because it's on both sides of the reaction, really. We know that. So H2O liquid is to be ignored. So now you are going to have this equation here, delta G equation, delta H reaction equation. You're going to use this equation to find the heat of reaction of our reaction number 1. Reaction number 1. Okay, that's what you are doing. So you have written down this equation here, and then you have this value over here. This value, heat of formation, and then this. And how many minutes should it take to do this? I don't know, 10 minutes, 15 minutes at the most. And after that, I have to remember that I have to keep on smiling. After 15 minutes, I start getting, the thing is displeased. The thing is feeling time is passing by. Okay, everybody is doing this right now. Go ahead and do it, and I'm going to not share the screen for a little while. If you have any question, you let me know right away. How is everybody doing? Okay, I need to ask specific people. Uh-oh. Did I screw up? Oh, there it is. Okay, let's go back to sharing screen. Gonzalez Soto Diago, how are you doing? Are you being able to calculate this? Speak up, please. Okay, all right. Zachary, how are you doing?
I'm fine.
Anoy, did I say? Mr. Marambire. Sarah,
Doing good.
Lisa,
I'm doing good.
Ethan,
Doing good.
okay, so I take it most of you are doing good. That's why you're not asking any questions. Why don't we do it this way? We take a 15-minute break now. Make it 18-minute break. We meet at 3:20 again. And if you want to keep on working or you want to take a little break or you want to print it out, this is a good time to do that. So we will meet again at 3:20. I'm going to turn off the recording. Otherwise, I'll be here. Some of the time I'll be available. Okay.
The recording has stopped.
Oh, oh. Okay. Let's get back together. All right, any questions?
This meeting is being recorded.
Any questions about how to calculate delta H and delta S? No questions. Or waiting for questions. I'm waiting for questions. Once you write it down correctly, it's a simple thing. Write down your equation to be used, and then just adding and subtracting and multiplying with moles. That's all.
Just to clarify on the entropy of sodium ion.
Entropy of sodium ion is given right here, 59 joules per K.
That-
There 8 is not there. That's a typo, you're right. Get rid of that 8.
And the units are kilojoules per mole, but since it's multiplied by mole, we just get rid.
Units of what?
What?
Units of what are kilojoules per mole?
The heat.
The heat, oh yeah, heat of reaction, yes, kilojoules per mole.
Yeah, but when we put it in the equation, it's 1 mole times the kilojoules per mole. And if we don't write the 1 mole, we can just
Yeah,
get,
you don't write it, that's okay with me. You just write down kilojoules. Don't write moles. Do that calculation in your head or do it on your calculator and just write down kilojoules. That's fine. So this version in the file, in the assignment is good. Let me check the version in the file that 8 should not be there. Let us change the whole file here. But you should be pretty much done by now. I'll change this file and then I'll ask everybody where they are at. All right, that's changed here. I'm gonna import that. Okay, that 8 is gone now from this file, at least. Files. Okay, assignment. Okay, that does it. Sarah, are you done with these two calculations? Alexander?
No.
Not done. Where
Just
are you?
curious.
Which calculation are you doing? Are you done with one? Delta H?
Did you guys get a negative or a positive delta H?
I got a positive.
Did you get positive 3.9?
Yeah, that's what I got.
All right, cool.
Okay, who needs help? Either you are done right now or you need help, one or the other. You cannot be any place else. So if you need help, you're gonna speak out and I'm gonna talk with you to help you. Who is that?
It's Josh, sorry.
Okay, do you need help?
I feel good. Thank you, Joe.
Okay. Who needs help? Help is available here. I guess nobody needs help. That means we're gonna go further now. Let's go further. Oh, good. Question, please. Sure, I can upload it as PDF, not a problem. Okay.
I guess it might be easier and as a print, but I just use like Google Docs. I pretty much just cut and paste, and then I just reformat. That's how I've been doing it. I also found out how, because for some reason, whenever I cut and paste into Google Drive, all the borders of the tables would disappear. But I just today figured out how to fix that. So if you guys need help with that, let me know.
Oh, you do. You did. Good for you. All right, let's see. So we're gonna save as. To make a PDF file for export, save as that. So I get this Word document file format. I go into that. It says save as PDF there. So I go there and export. And it says Word is converting. So that I should have it over here now. Today is 3/28, balancing H and X. And I'm going to now export this file. Into files. Upload. Okay, there we go, PDF. Choose for upload. And here we have it. All right. Hooray for modern technology. I mean, you know, it's quite something to just take a document and move it from here to there. Yes, very easy, but I mean, you think about all the things that are involved in there. Wow. Okay, who else has a question? Nobody else has a question. Okay, let's talk about it more then.
I'm gonna. I actually stepped away for a sec. I'm gonna calculate delta S right now, and then I just want to see if anyone else got the same.
Okay.
Did anyone get 24 joules over Kelvin times mole?
Yeah, folks, what are the answers you are getting?
For delta S, I got 44 joules per Kelvin.
Okay, did you just do, you did reactants minus products, right? For
Products minus reactants.
Yeah, products.
Product is the final and reactant is the finished.
And that would be,
Yeah, so it'd be 59 plus 57 minus 72.
oh yeah, I don't, somehow I did minus 92 instead of instead of 72. Okay, yeah, that makes sense.
Yeah, it's so easy to make these little mistakes. Yep, I have seen that before. Okay, anybody else? Nobody else. Then you guys are going to start. Then the last thing to do is to find delta G. And that's very simple. It's a simple equation than that right here. Delta H minus T delta X. T is 25 degrees Celsius, 298 Kelvin. 298 Kelvin is T. That's what we know because the superscript 0 tells us that you have the value of delta H, you have the value of delta S, and you put it in there, and you have the value of delta G, and this should be negative here. Then, yeah, okay. That's a mistake again. Then, see what I mean by I have to be perfect, and that often doesn't work. A little bit mistake here just doesn't work. Okay, so this is easy to do. So now I want you to start doing the experiment and write down this here. Data and results table, NaCl, NaNO3, and Na2CO, sodium acetate, and mass T1, T2, delta T, and then you can calculate it. So this is the part of the experiment. So you're doing that right now. And if you have any trouble, you let me know right away. Jesse, how are you doing? Mr. Carpio,
I'm good.
Miss Carpio, I'm sorry.
What did you guys get for Delta G?
Delta T?
Delta G.
I got negative 9.2 times 10 to the third joules or negative 9.2 kilojoules.
Perfect. That's what I got too. Sweet.
I'm sorry, but is that Mr. Carpio or Miss Carpio? I can't tell.
It's Carpio.
All right, thank you. So everybody is doing this okay. They are understanding what's going on, and they are doing the experiment right now. And everybody is able to do the experiment. All right, good enough.
I actually, my Beyond Labs isn't working for some reason. I can't get in.
You can't get a what?
I can't get in for some reason, so I'm working on maybe changing the password.
Okay, if that doesn't happen in 2 minutes, let me know and we can find something else to do.
Yeah, it's still not letting me in. It says it can take up to 30 minutes.
Okay, let's do it this way then. I'm gonna open it up and you're gonna tell me what to do. Did you print out this, Sarah, by any chance?
I printed it out, yes.
Oh, good. So what I'm doing now, you will see what I'm doing, of course. My computer is not working well either, I guess. Oh, there we go. Okay. Ah. I don't want to go there. It disappeared. Okay, here we are, Sarah. Tell me what to do.
So you're going to take the bottle of sodium chloride, weigh a paper.
Okay, so that's already weighed over there. Write down the number, grams.
So I have 1.9871.
Yes, ma'am. What do I do now?
And then it says to the calometer will be on the lab bench and filled with 100 ml of water.
So this is 100 ml of water in it. Okay.
Yep. Make
And
sure the
then the-
stirrer is on.
So what is going to be the mass of the system?
The mass of the system would be 101.9871.
Very good. Now I dump this sodium chloride in the calorimeter.
And then you make sure that the stirrer is on.
The stirrer is on. I can see it's going back and forth. Okay, good.
In the thermometer window, you should click save to begin recording and allow
Okay.
20 to 30 seconds to
Okay.
obtain a baseline temperature.
All right.
Then you click stop.
Collect the stop.
It says then you click stop. Yeah.
Well, we have not put the NaCl in there yet.
Oh, that's right. So drag the weighed paper to the sample with the calometer until it snaps into place and then pour the sample into the calometer.
What's the mass one more time?
101.9871.
Oh, is the temperature is decreasing. That's interesting.
100
We
grams.
started out with 25.00. So write that down. 85. Now we are looking for decreased temperature, the lowest temperature, 84, 82. 81. 80. Sorry, what?
Yeah.
Yes,
I think it's 100 milliliters water, right?
right. And then we
That's
put
a 1-to-1, so it should be,
NaCl in it, so 101 point something.
yeah.
Right. 100 milliliter equals 100 grams, yes.
You could hit the accelerate if you wanted.
Okay, hit the stop.
If it's leveled out, which it looks like it has.
Yeah, it looks like it has. Okay, so we have saved. Now we have to get rid of this, so we're gonna get rid of that. Okay, what do I do now?
And then you hit click stop, and then you hit the red disposal bucket to clear the lab.
Got it, done, very
Then
good.
you're gonna click on the stock room to enter.
Okay, and then we're gonna look at this. Which
Yep.
experiment do we want now?
You wanna click on solution NaAC and repeat the experiment with NaCH3COO.
So that's sodium acetate. They have a fancy way of writing it.
Yep, NaAC.
So the first one is NaNO3.
The first one is NaCl.
We are already done with that, right?
So the next one is NaAC.
It is the next one?
Yes.
Okay, well, doesn't make any difference. Okay, here we go, NaACS. That means sodium acetate, okay?
Okay.
Now we do the same thing. We have, we stop or we say save, and then we go put this into the calorimeter.
What was the mass on that?
Oh, let's write it down.
Yep.
2.0195 grams.
So 102.0194.
Yes. And also we also know the mass of the solid, so that's good.
So it's the mass of the solid is 2.0194.
Yes. Grams. Now this one is an exothermic reaction. That was an endothermic reaction. This is exothermic. All right, almost there. 90, 2591, 25.92, 93, 94, 95, anybody? Oh, 95. Okay. $96. I guess that's it. 25.96. Okay, we're gonna dump it. There is our thing dumped. Now we go back over here. We check over here. We did AC. Now which one we are doing now?
NaNO3.
What is the name of it?
It is sodium sodium nitrate.
Good.
Nitrate. Yes.
Yes. Okay, dump it. 2.0578 grams.
2.0578. So
Nine,
that's
sorry.
9. So that's
Yes.
102.0579.
Yes.
Starting temperature is 25 degrees.
Okay, we're gonna, yes, starting current temperature 25 is fine. This one is very quickly going down the temperature. Look at that. An endothermic process.
So 24.00?
23.99.
23.99. Okay.
All right, that part is done now, okay? You do the rest.
Yes.
Other people could have also written it down, that's fine.
Perfect. Thank you. I use those values as well.
Now, your time to do the calculation and my time to answer questions. So keep on working and you might be done with the lab today. And if you want to do something else, you have any questions? Well, go for it. Other questions besides lab. This is a good time to do questions.
So would it make sense for Q for the first one to be negative 85.38?
Why would it be negative? Is it?
Because the initial T was 25 degrees and the final T was 24.8.
So it was a.
So the delta T is negative.
Exothermic reaction or endothermic?
That would be an endothermic.
And so heat went into the system or out of the system?
Oh, it went out of the system, so it'd be exothermic.
Endothermic, you said endothermic.
I know, it's an exothermic.
Did the temperature
Decreased.
decreased?
Yeah.
This is endothermic. That
Endothermic,
means
yep,
it went into the system.
yep.
So that's positive.
No, it decreased.
Yes, heat decreased, so it went into the system, right?
Yeah. So, okay, maybe I have to look up how to do delta T again.
It should just be, is it final minus initial?
That's what I thought. So
Final
final,
minus initial, 24.8 minus 25.
so
Yeah.
that's negative 0.2.
Yeah, that's right, negative.
That's for
So
delta.
would it, so for that first one, Josh, would it be negative 85.38?
I actually don't, are we given the heat specific capacity?
Well, you-
4.184 is the
Oh,
water.
is that- Okay,
You for water.
But it would be positive because Q.
well, let's see right here, let's see.
Because Q equals mass times delta T times C, right?
Yeah,
So our mass is 101.9871
mhm.
times by -2 times by 4.186.
Yeah, well, on my calculator, it ends up being positive. But yeah,
How?
that's a good question.
Because it's only one negative, right?
Yeah, Q should be positive. I don't think, actually, no.
Right? I don't know.
Yeah, I think it's negative 81.1.
80. Did you get 81.1? 9871 times by 0.2 negative times by 4.186. 85.338.
4.184.
4.186. That's
No,
what I have.
184.
184. Well, then Suri lied to me.
And the grams was 101.9781, right?
101.9871.
871.
And then the next experiment was 102.0194. And
Mhm.
then the next experiment was 102.0579. Now, Professor, the molar mass is the molar mass of the entire equation, right?
Molar mass is molar mass of a compound. Equations do not have molar masses.
So just the molar mass of NaCl.
That's right.
Okay.
You said you got 85 for Q? I keep getting 81. I don't know why.
101.9871 times by, because our initial temperature was 25 and our
Mhm.
final temperature was 24.80. So that means it's 101.987 grams, which would be the mass, times by -0.2, which would be the delta temperature, times by 4.184, and that's negative 85.34.
Maybe there's something wrong with my calculator. Yeah, it's just giving me a different value. I'm typing in that something. I'll try it on my phone to see if it's different.
Maybe it needs a battery.
No, I'm still getting 81.
Really? Let me try it again.
But I'm doing my delta T was 0.19 instead of 0.20. Maybe different.
Well, that will make the difference.
So did you get 24.81 or 80?
8.1.
Yeah, see, I have 80.
It can be a little different. That's okay.
Yeah. For Q, I got negative 85.34.
All right. I'll just do 0.2 also.
And then so negative 85.34. And the molar mass of NaCl is 58.35. So, so then divide that by 58.35. So I got negative 1.463 as my experimental delta H.
Okay, you guys are doing okay. I'm gonna stop sharing. I'm still here. You folks are doing okay. All right.
Hey, Professor, do you mind if I
Yes.
just grab molar masses from the internet, or do you want me to use the periodic table in the back of the guidebook?
Well, it doesn't matter. You know how to do molar masses.
Fair enough.
You just write it down, molar mass. You don't need to show me how you calculated them. You don't have to show me how to calculate molar mass anymore, okay?
Sounds good.
Just write it down.
I'll still do units though.
Now, I have a problem that I want to discuss with you guys. Everybody, I have a problem.
What's going on, Professor?
The problem is the reaction with NaOH or NaCl and NaNO3, the temperature decreased. Is that right?
With NaCl, the temperature decreased.
With NaNO3, it's also decreased.
Yes.
That means it's an endothermic reaction. Heat went into the system from outside. In order for the system to be at 25 degrees Celsius again, the system would absorb heat from the surrounding. So this is an endothermic reaction, and therefore the sign of Q is supposed to be positive. But when we write 0.1, negative 0.1 delta T, then Q becomes negative. I don't know how to deal with that, except I have to tell you, you have to write positive Q. You cannot write negative Q.
In the endothermic reaction, we put negative Q.
No, we put positive Q for endothermic reaction.
Exothermic. Sorry.
Exothermic, we put negative because it went out of the system.
Yeah, but in the equation we put negative Q. If you put negative Q for here too, it would cancel out the negative on the endothermic.
So endothermic is Q is positive and delta H is positive. So when you write down the equation Q equals C multiplied by delta T multiplied by gram, then because delta T is negative, you get negative Q. And I don't know what to do with that because it should be positive Q. It cannot be negative Q. So you are going to write positive Q, not write negative Q, even when the equation shows you negative Q. I don't know what to do with it, but this is what we have to do. I don't know how to reconcile the two things which seem to be opposite to each other. So please, for endothermic reaction, Q is positive. And two reactions are endothermic and one is exothermic. So write the symbol of Q accordingly, not according to what the calculation says.
Okay, so Q is positive.
Endothermic Q is positive. Exothermic Q is negative.
So going forward, is that that's weird, but okay.
Yeah, I know. I don't know how to reconcile that, but it has to be positive for endothermic.
Hey, Lisa.
Yeah.
How did you end up getting 58.35 moles?
The molar mass. So grams over molar mass, right?
Well, so molar mass is grams over mole. So the way I did it was I just took the total grams that the mass given.
So the 58.35 or 58.35. This is for NaCl, right?
Yeah. Wait, I got 101.9871
NaCl?
for NaCl plus H2O.
Well, because you're not doing the molar mass of H2O. NaCl. Yeah, it's a 1-to-1.
We are not doing molar mass of water. That's right. So
Oh,
it's
so we're just-
58.45.
Okay, we're just doing the one. Okay.
Na is 22.99 plus Cl is 35.45. So 58.44. 35 I would take because it's just, how do you do the sig fig?
Professor,
Yes.
to find the sign of delta G, you have to look up the entropy of the ions of the other two.
I did not understand that.
To find the delta G, the sign of, we'd have to look up on the internet the entropy of like sodium nitrate or the ions of sodium nitrate and
Did I give it to you? I thought I gave it to you already.
the delta S of Na ion and sodium ion and chloride ion.
Right. And NaCl separately for solid.
What about the
No.
other reaction?
I'm checking. NaCl solid is there, 72 joules per Kelvin multiplied by mole. Na ion and so chloride ion is there, so that is already there.
But what about for sodium acetate and sodium nitrate?
That you'll have to look up.
All right.
So you will have to look up sodium acetate solid, sodium ion, you already know sodium ion, right? So sodium ion, you don't have to look up. Nitrate ion and acetate ion, well, that's what you need to look up. And solid sodium nitrate and sodium acetate. And you have to look up the heat of formation. The sodium ion is already there, so same for all sodium ions.
Are we still working on whether Q should be negative, positive, or are we just playing it as positive?
If it is an endothermic reaction, we're gonna put it at positive.
Okay. And if it's exothermic,
It's gonna be negative.
so we just, okay.
The temperature increases is exothermic, if the temperature decreases is endothermic.
So if the temperature increases in the reaction, Q is going to be
Because
negative.
of the reaction,
Okay.
it's exothermic.
So the NaNO3 solid plus H2O, that should be a negative value for Q.
The NaC2H3O2,
Mm-hmm.
is that the one you're talking
Sodium
about?
acetate,
Sodium acetate?
what happened? Temperature increased,
The temperature, yeah,
so then it's negative.
so then it's negative.
Yes.
Wait, didn't the temperature decrease for the,
No, because remember we did them opposite, so you got to switch those graphs. So the initial temp was 25.01
Mhm.
and the final temp was 25.95, and it's the only one that the temperature went up.
Oh, not for the sodium acetate, right? For the sodium nitrate?
I don't know, Professor, did I get that wrong?
I did not write it down. You
Sodium-
guys wrote it down.
Sodium acetate, so it's exothermic.
And
Sorry.
if you are in doubt, for most people, it's very easy to go back there and do it right away. It doesn't take much time, as you know.
Okay. What was T2 for the sodium nitrate calculation? I could go back and solve it, but I'm pretty sure we have it written down. Someone does.
Well, I have it written down, but I'm wondering if it switched, because I remember we did it in order. We did NaCl, then we did NaC2H3O, and then NaNO3. Yeah.
That's it. Yeah, you're right.
So I'm thinking that the only one that went up is the NaC2H3O2, which means, Professor, that's an exothermic reaction.
Yeah, that's correct.
Which means that that's the only one that's negative.
Yes. So it's positive, negative.
So even though the temperature went up, it's a negative, whereas all the other temperatures went down and it's a positive.
Yeah, because temperature went out of the system, making the surrounding hotter.
Ah,
So when you're measuring the temperature, like feeling it, it's surrounding.
so is it negative Q equals mass times delta T times specific heat?
That would flip the sign, so I think that would solve it.
Okay.
For which one? For the first one, for delta H, I got 1.46 joules over mole. How did you just divided by moles, right? You divided Q by moles.
Oh, you.
Okay, just let me know. I'm trying to still figure it out too, so don't take my answer for it, you know.
Yeah, how did you do it?
What was your Q, Joshua?
My Q for sodium chloride was 85.34 joules, and then I divided that by, so I took the molar mass of NaCl, and it's a 1-to-1 reaction, so you're left with the molar mass doesn't change, so you end up with 58.44 moles, and then I just divided joule by the moles.
Great. I thought it was the mass of NaCl at the start that you measured multiplied by the molar mass to get the moles.
That's not a bad strat either. I mean, that makes sense too. Actually, I think because then you'll go grams. Yeah, that actually makes sense.
Professor, is that right?
What?
Do you do the mass of the NaCl times the molar mass to get the
Yeah,
Not
To
times
get-
the molar mass, divided by Q divided by molar mass.
but how do you find the molar mass? Is it just the 58.35?
Yes, the molar mass. You know how to find the molar mass. Yeah.
he's asking, Professor. So we get the molar mass, and that's grams over mole. To get moles, we're multiplying the initial grams of NaCl by moles over grams, so we're left over with moles.
That's right. Moles over grams. Yes.
And
That's right.
and we're just doing the grams of the NaCl added, correct?
Right. NaCl, we have 1 point some grams, 1.9 or whatever it is.
That makes sense to me.
So how,
gram cancel
what's-
out. That's right. And moles
Josh,
is left over.
what's the formula?
So pretty much you're taking the grams of NaCl, so you just subtract our mass by 100, or you can just take the last digits.
Okay, so 1.9871,
That's grams, Na solid.
right?
And then you're multiplying that by the found molar mass, which is 58.44.
Okay.
You know how to convert grams to moles. All of you do.
That's what I was doing initially too, but I did it. I don't know. I confused myself.
So then you take Q and you divide Q by that.
By the moles.
Okay.
I see where you got that answer too, though, Lisa. I mean, it made sense to me.
Oh, I just want to do it right. I don't know. Q. So then the experimental heat for the first one will be like 0.7345, right?
I'll do the math right now.
49.
Actually,
0.73.49. Okay.
for delta H,
Yes.
what did you guys get for moles of NaCl?
116.12.
I didn't. You're dividing the initial grams by 58.44, right?
It's about like 2 grams divided by 58.
Yeah.
Just grams to moles. Oh, yeah.
Oh, so then that's not it at all. So then
Like
Yeah.
what?
Moles?
3, 4.
Yeah, I got 0.034 moles.
Yeah,
then
but I just got 2.
I got 2,510.
Yep, that's what I got too. Is that what everybody else got?
So dividing, so you divide the initial grams of an ACL by the grams of the molar mass. You're pretty much just what's the terminology for that? Sorry.
Hey, Professor, are you going to be in there at 5:45?
Yes,
Okay, what time does class end? I forget.
it's pretty much ending now. But 10 more minutes is okay because we start 10 minutes late.
Okay, I'm going to see you at your meeting.
Okay, good.
Okay, thank you.
Okay, bye.
I'm not able to make it. I'm not able to make it to the office hours. If any crucial information comes out that helps, could you send it my way?
I got you.
Awesome, thank you.
Uh-huh.
Okay, if you want to go, you can say bye. If you want to stay around for 4 or 5 more minutes and you have questions, let me know.
I feel like we lost some people this lecture. There's not too many people.
I know there are not too many people. What can I say? And then
Go ahead. Yeah. Yeah. And then that should be joules over mole.
And that would be 2.5 kilojoules.
Yeah. Professor, you don't mind if it's in kilojoules or joules, right? For delta H?
we want it in kilojoules.
Okay.
I wouldn't call it wrong. I wouldn't take away points, but that's what we want.
Hey, Professor.
Mhm.
Would you say that like entropy, enthalpy is probably one of the harder concepts in chemistry 1A?
Yes.
Do you think it's the hardest one, or is it going to get harder?
It's pretty challenging. Not too many things are as challenging as that one.
I just feel like overall, it's not the calculations that I'm confused with. It's like the fundamentals of it, like
So you need to write down those definitions.
Yeah, I think I'm trying to do I'm doing some like separate research, and I have one of my old chemistry textbooks, so I'm just trying to brush up.
Okay. We have those definitions written down. You have definitions in your head.
Mhm.
That really helps.
All righty, well, I think I'm good. I will see you next Monday, Professor. Adios, everyone.
All right. The quiz is going to be next week, not this week.
Beautiful.
Probably Tuesday.